So this is the 45th session on relative velocity. In this session, I will discuss the relative velocity problems for mutually translating frames, case 1. For knowing what is case 1, you just refer to the videos 42, 43, 44. Okay, you will get all the details of case 1. For mutually translating frames, we are going to discuss the problem of case 1 for mutually translating frame. Case 1, case 2, case 3, case 4 all have been stated in video 42, 42nd session. If you go to the video 42, you will get all the details. Okay, I'll write down the problem. Fine. Raindrops are falling downward at a speed of 6 km per hour with respect to ground in a direction perpendicular to an inclined plane, which makes an angle of 30 degree with the rightward horizontal. A man holding an umbrella runs down the incline at a constant speed of 4 km per hour with respect to ground. At what angle with the downward vertical should the person hold the umbrella to protect himself from the raindrop in best possible way? Okay, this is the question. Fine, I'll rub it. Okay, I'll rub it. Huh? So now, first of all, what we do, we complete all the formalities. What is the object under consideration? Raindrop. So raindrop we denote by what? R. Instead of M we have man frame, that is noted by M. Instead of F we have ground frame, we denote it by G. Alright. Then we write down the vector equation. VRG is just equal to VRM plus VMG. Now again VMG complete information is there, magnitude, direction both, 4 km per hour down the incline. Here also complete information is there, given 6 km per hour, normal to the inclined plane. Magnitude, direction known completely. Regarding VRM nothing is known. Therefore, it's a problem of case 1. It's a case 1 problem. It's a problem of what, Poliye? Tell. Case 1 problem, alright. Now what we do, first we draw the diagram of the situation. So see, this is the horizontal, rightward horizontal. This is the inclined plane. This is 30-degree angle. Now raindrops are falling at right angle to the inclined plane. Raindrops are coming like this. So now from this, one more thing, you see this vector equation. So VRM is just equal to VRG minus VMG. That is just equal to VRG plus minus of VMG. Alright. Now VRG, we have to add these two vectors by parallelogram law of vector addition. Now VRG is this one. This is VRG. Right angle to the inclined plane. This is equal to 6 km per hour. It right angle to the inclined plane. So from vertical by geometry to make an angle of 30 degree. Because it's right angle to this, it has to make a 30-degree angle with the downward vertical. Is it alright? 30 is okay. Fine. Now VMG is what? VMG is downward 4 km per hour. So minus VMG will be what? Upward, up the incline. Reverse the right concept. I'll rub this one, okay? Because there is no space left, so I'll write it down again. So minus VMG is 4 down the incline. Minus VMG is 4 up the incline. This is equal to 4 km per hour up the incline. Now VRM is the vector sum of these two velocities. So what do? We take these two as adjacent side. We complete the parallelogram. This one. Now the diagonal of this parallelogram through the common tail of these two vectors. This is VRM. Okay. Now in order to protect himself from the raindrop in the best possible way, the person should hold the umbrella axis along the direction of VRM. Alright. So suppose VRM makes an angle of say theta with a downward vertical. This theta we have to find out. Alright. Now question is how to find the value of theta. That is the question. So first what do? We find this angle and then add 30 degree to it, we get the value of theta. Let's call this angle as phi. So this angle we see that theta is equal to 30 degree plus phi. Theta is just equal to 30 degree plus phi. That is the value of theta. 30 degree plus phi is the value of theta. Now how to find, to determine theta we have to know phi. Now to determine phi is an easy thing. It's a rectangle, you can see this is 4, this is also 4, this is 6. So this is a right angle triangle. So tan phi becomes how much? Tan phi becomes this by this. This is 4, this is also 4, rectangle. Opposite sides of rectangle are equal. And this is 6 km per hour. So 4 by 6 becomes 2 by 3. So phi becomes tan inverse 2 by 3. So theta becomes 30 degree plus tan inverse 2 by 3. Therefore it is the required answer. Alright. So theta is equal to 30 degree plus tan inverse 2 by 3. That is therefore the required answer. Alright. This is the answer to the first part of the to this question. Okay. Now what I'll do, I'll take up one more problem on this phase 1, case 1 of mutually translating frames. Alright. So this I'll rub, alright. So I take up one more problem, case 1 on mutually translating frames. Alright. So I take up one more problem. And now I'll write down the problem. Fine. So now the question is this. The windscreen of a car moving rightward at a constant speed v with respect to ground makes an angle of theta with the leftward horizontal. With the leftward horizontal. With the leftward what? Horizontal. Ice blocks are falling vertically downward, at a constant speed u with respect to ground. At a constant speed u with respect to ground. The driver of the car observes the ice blocks to bounce vertically upward after elastic collision with the windscreen of the car. Find the relation between u, v and theta. We have to find the relation between u, v and theta. All right. Is it clear? Fine. I'll grab it, okay? So now what I'll do, first I'll identify the frames and object. So object under consideration is simply ice blocks, which is denoted by say P say. For intermediate frame we have the car frame, which is denoted by C. For frame F we have ground frame, denoted by G. Okay, fine. For ground frame denoted by G, car frame denoted by C, and for ice blocks denoted by P. Now what do? We write down the vector equation. VPG is equal to VPC plus VCG. Okay. So what is VPC? Velocity of ice block with respect to car. That is VPG minus VCG. That is just equal to VPG plus minus of VCG. Now we have complete information of VPG, ice blocks, ground frame, u speed, downward direction, magnitude direction both known. Velocity of car with respect to ground, v, rightward, magnitude direction both known. Nothing told about this one. Definitely it's a problem of case 1. It's a problem of what? Case 1 problem. Alright. It's a problem of case 1. Alright. So now what I do, I will first draw the diagram. The side view of the car going rightward. So this is, I'll not draw the complete car, I'll just draw the relevant part of it. Okay. So this is the windscreen, alright. This makes an angle of theta with the leftward vertical as leftward horizontal as stated just now. This is the bonnet of the car. This is the side view, okay. I have not drawn the complete car. Now this car is going rightward at a speed v, rightward with respect to ground. And ice blocks are falling downward like this with a speed u with respect to ground. This is the ice block, one of the ice blocks. This is one of the ice blocks, okay. And this is the car going rightward at speed v. Alright. Now first what we do, first of all what we do is that we find the direction of motion of ice block as seen by observer in the car. That is, we find the direction of the vector VPC, velocity of ice block with respect to car. So VPG and minus VCG, alright. So VPG is what? VPG is this V. So this I'll draw here, okay. This is V. Velocity of VPG and VPG and VCG. VPG is nothing but U downward. This is U downward. And VCG is V rightward, minus VCG is V leftward. VCG is V rightward, minus VCG is V leftward. This one. And if we add factorially these two quantities, we get the direction of VPC. So with these two as adjacent side, we complete the parallelogram, which is a rectangle. Now the common tail, diagonal through common tail of these two vectors, this one. This vector is VPC. Now this angle let us assume to be phi. This is a right angle. So tan phi becomes this by this. Tan phi becomes, this is U, this is V, this is also V. Right angle triangle. Tan phi is equal to U by V. Alright. So an observer in the car will observe the ice blocks to be coming like this. If driver is sitting here, he will see ice blocks are coming like this at an angle phi with the rightward horizontal. Alright. Ice blocks are coming like this at an angle phi with the rightward horizontal. Alright. So now what we have to do? Now, point is this. Say, for just consider a particular ice block coming here. Now it is clearly stated that after collision, elastic collision with this windscreen, the driver of the car notices the ice blocks to bounce vertically upward. Alright. So this means something like this. I'll draw the windscreen here again, okay? See. After collision, one of the ice blocks moves vertically upward as seen by an observer in the car. An observer in the car notices that after elastic collision with the windscreen of the car, ice block bounces vertically upward. Alright. Ice block bounces what? Vertically upward after elastic collision with the windscreen of the car. Okay. So this is the direction of motion of ice block just after elastic collision with the windscreen of the car as noticed by the driver of the car. Okay. Now tell me one thing you must know. If a surface is fixed, an object hits it elastically, then angle of incidence and angle of reflection are equal. I'll state it again. This is a fixed surface. An object hits the surface at some angle, not necessarily at right angle. It hits the fixed surface at some angle, rigid surface. This is a fixed rigid surface. An object hits the surface elastically and bounces back. This is the normal to the surface. This is the angle of incidence. This is the angle of reflection. If surface is fixed and collision is elastic, then angle of incidence, angle of reflection are both equal. Okay. Now see, in the frame of the windscreen is fixed to the car. The windscreen is attached to the car. With respect to car, the windscreen is fixed. So with respect to observer in the car, the windscreen is fixed. Now the hailstorm is undergoing, ice block is undergoing an elastic collision with the windscreen. So this means angle of incidence equal to angle of reflection. This concept will be varied here also. Now how to determine the angle of reflection? We draw a normal to this windscreen. So this will be by geometry, this angle will also be how much? Theta. So angle of reflection, angle made by the velocity of hailstorm ice block with respect to car just after collision is theta. That is the angle of reflection. Now as seen by observer in the car, the windscreen is fixed, surface is fixed, rigid surface, fixed surface, elastic collision, angle of reflection is equal to angle of incidence. This is the angle of reflection. So angle of incidence should also be same. So just before collision, this ice block must be coming something like this. This will be the angle of incidence theta. That will also be theta as I explained just now. So this angle is equal to what? Phi. So this is alright. So now what do we see from this? This right angle. So just before collision with the windscreen of the car, ice block is appear to coming in this direction. And just after collision, as seen by observer in the car, the ice blocks bounce in vertically upward direction. So theta is the angle of reflection. With respect to observer in the car, this windscreen is fixed. Rigid windscreen surface fixed. Elastic collision. Angle of incidence equal to angle of reflection. So theta is the angle of reflection. Theta is also the angle of incidence. And this is phi. So just before collision, an observer in the car notices the hailstorm, ice blocks to becoming something like this. So this is theta, this total is 90 degree. So this angle will be how much? 90 degree minus 2 theta. That is equal to phi. Okay. So tan phi, will take the tan of this. Tan phi is equal to tan of 90 degree minus 2 theta. Tan 90 degree minus 2 theta is how much? Cot 2 theta. Now tan phi is how much? U by v. U by v is just equal to what? Cot of 2 theta. This is the required relation between u, v and theta. Fine. So now here till here I have discussed 4 sessions I have taken on relative velocity problems for mutually translating frames for the problem of case 1. So case 1 is finished here. Alright. Now in next video I will take up case 2. I am again repeating, to know case 1, case 2, case 3, case 4, just refer to the 42nd video. 42nd session on relative velocity, you will get all the details there. Okay. So here phase 1 is finished. Case 1 of relative velocity problems for mutually translating frame is hereby over. Alright. So I close it here itself.